Hi, everybody. Let me share my screen. So thank you, Guido, for your introduction. I'm Marco Venere, and today I will talk about quantum error mitigation applied to a QAOA workflow. In particular, this project has been made in collaboration with the Quantum Open Source Foundation. But let's start from who I am. I'm a PhD student at the first year in information technology here at Politecnico di Milano. And concurrently, I'm also a research intern in AMD and have been a student member at the Quantum Open Source Foundation. My main research interests are related to quantum computing with quantum error correction and mitigation, and computation on quantum circuits and their optimization, high-performance computing with the design of advanced heterogeneous architectures, and other design with FPGAs. And today, we will talk about quantum computers. They exploit laws of quantum mechanics to achieve a super polynomial speedup with respect to classical computation. In particular, the unit of information is the qubit, which may stay in two possible states at the same time, thanks to the superposition principle. This principle, together with other effects like entanglement, allows us to get exponential speedups in a lot of interesting use cases. And today, I will talk about one of these use cases, which is combinatorial optimization. In particular, I'm referring to an algorithm called quantum approximate optimization algorithm, in brief QAOA, which solves combinatorial optimization problems. It receives an input problem with this following formalism, where you have an objective function f of x that you want to minimize, subject to some very specific constraints. Starting from this formalism, we define a quantum circuit, which is called in jargon ansatz. It describes all the possible operations to perform on the qubits. As you may notice, this circuit is parametric. Indeed, it must deal with betas and gammas parameters that must be tuned in order for the circuit to give as output the correct solution to the problem. To perform such a tuning, we use an optimizer. State-of-the-art has a number of possible optimizers to consider, and in this work, we are considering in particular Kobila, Powell, Nelder-Mead, and fake nodes. Well, this process seems easy, but telling the truth, it's really not. Indeed, quantum computers must deal with noise. Here you can see a graph representing the quantum processing unit of a well-known quantum computer, which is the IBM Q16 Melbourne, and its physical constraints. In particular, all the nodes represent qubit, and as you notice, there are numbers associated with these nodes. Indeed, they represent the error rates for operation applied on a one qubit, and also the readout of its value. In addition, we can see on the edges other numbers which represent error rates for a two-qubit operations applied to a specific pair of qubits. These errors deteriorate the final quality of the output of the algorithm in such a way that QAOA becomes not practical at all. Therefore, the research objectives of this work are firstly to mitigate the effects of noise, in particular using some state-of-the-art techniques for error mitigation. Also, we want to perform an effectiveness analysis of this approach to see if it is really functional for two well-known optimization problems, which are the maximum cut problem and the knapsack problem. Let's start with the first point. One of the most important mitigation technique is the zero noise extrapolation. Let's imagine that we have a circuit that we want to mitigate. And in particular, looking at this circuit, let's focus on these gates. These are the quantum equivalents of the negation belonging to digital circuits, like the NOT operator. And as everybody knows, two negations cancel out. So what we can do in this circuit is we can add pairs of these negations. And as you may imagine, the final output of the circuit is just the same as the first one because they are functionally equivalent. The difference is just that the circuit is longer. We can keep on replicating these gates and producing several different circuits, each one being longer and longer than the previous one. All of them are functionally equivalent, but this difference in the depth of the circuit implies that they are more and more affected by noise. What we can do then is we can measure out these circuits, and since their output is probabilistic, we compute the expectation value of their output, and we plot it. As you can notice, here we have the expectation values as the length of the circuit increases, and so as the noise intensity increases as well. In this way, we can extrapolate what happens when zero noise is applied to the circuit. This extrapolation will produce the mitigated expectation value. That will be the correct output of the quantum circuit. Well, we introduced this technique into QAOA, and in particular, we modified the optimization step. Indeed, the optimizer will not receive as input the generic original quantum circuit, the ansatz, but its modified version after applying the mitigation technique. We are using, in a technical sense, openQAOA, which is a state-of-the-art framework to run QAOA problems, and Mitiq as a state-of-the-art library to perform zero-noise extrapolation. Now that we have seen the integration process, let's focus on the effectiveness analysis to see how the optimizer behaves as we apply this integration. We'll consider, as I told you before, the maximum cut problem and the knapsack problem. And since openQAOA and Mitiq are frameworks that both have several parameters, we perform an exploration of the parameter space in order to find out the effects of our work. Let's start with the instance of a maximum cut problem. Here you can see the same instance given as input to do two different optimizers, Kobila and Powell, in a noiseless case. As you can notice, Kobila only requires 200 iterations to reach the solution to the problem, while Powell requires more than 3,000. While their solutions are comparable, the execution time required by Kobila is significantly reduced with respect to Powell. So we will pick this option for our study. And we apply noise. As you can see, the performance of Kobila after applying noise are way different. Even though the general trend of the exploration of the space is quite similar, the final values of the objective function are way higher. And since we are doing a minimization problem, this means that the final quality of the output is lower and reduced. So what we need to do in this case is to apply zero noise extrapolation. Let's test two different extrapolations techniques shown here in green. On the left side, you can see the exponential extrapolator working on. And as you can notice, even though it initially overlaps with the noisy trend of openQAOA, in the very end, it reaches a lower solution. This means that the mitigation technique is actually working. On the other side, the linear extrapolator completely overlaps with respect to the trend given by the noisy case. This means that we are not reaching any valuable effect thanks to this method. Let's now move on to another case with the knapsack problem. After doing the extensive exploration of the parameter space, we found that Kobila is the best solver. We apply noise, and we see what happens when the zero noise extrapolator is performed by using the exponential extrapolator and the fake nodes extrapolation. As you can see, the exponential extrapolator does not really follow the trends of openQAOA. Indeed, after modifying the parameters, the optimizer gets stuck in a local minimum, which is way less efficient than the local minimum found by the noisy openQAOA. This means that even though we are technically mitigating the effects of noise, we are altering the exploration of the parameter space in such a way that we cannot really go to the correct solution to the problem, but just to a local minimum, which is very inconvenient. On the other side, the fake nodes extrapolator completely overlaps with the noisy case. As a final conclusion, we can consider the effects of zero noise extrapolation as very case-dependent. They are really based on the specific instance of the problem, and we cannot really generalize. Even though there are cases where the effects of zero noise extrapolations are meaningful, there are other cases in which they are disruptive, and they really make us vary further from the correct solution to the problem. In conclusion, we tested the integration of zero noise extrapolation in a QAOA framework, and we also evaluated the effectiveness of this approach with respect to two well-known optimization problems. And as next steps, we want to consider a further mitigation technique, which is the probabilistic error cancellation. Also, we want to evaluate the effects on another very important optimization problem, which is the aircraft loading optimization. Finally, we want to test the same framework on multiple quantum processing units. Also, I would like to talk about my future research direction. In particular, I will work on a focus on a workflow for the compilation of quantum circuit, and in particular, we consider the optimization of the circuit and the mitigation of the error by viewing also multiple QPUs. And I will even consider advanced heterogeneous architectures that will involve the quantum processing units to get further acceleration and speed up. I'm also available here for any research internships and visiting periods. With this, I thank you all for your attention, and I'm here available for any question.
Thank you, Marco, for your talk. I have a question. You talk about error mitigation techniques, but we know that in the quantum world, there are also error correction techniques. So yes. Can also error correction techniques be applied to QAOA workflow or just error mitigation? And if you can briefly explain the difference between the two techniques.
Yes, thank you for your question. It's very interesting. Indeed, they can be applied to a QAOA workflow. In the error mitigation case, what we are doing is we are using statistics and probability to try and figure out what is the correct output of a quantum circuit. While in the error correction case, we exploit some ancilla qubits that are inside the QPU, we measure them, and we try to understand the specific errors that have occurred inside the algorithm. And to do so, we want to undo the effect of noise. There are some possible algorithms to do so, like the minimum weight perfect matching or the union find, which are decoding algorithms, because given the measurement of these qubits, they can decode it and provide a correct solution to the problem by undoing the effects of noise. And they're mainly performed on FPGAs. And here in NextLab, we are also focusing on the acceleration of decoding algorithms in order to enable further and further quantum engineers to make the usage of quantum computers even more practical.
Okay, thank you, Marco. So
if
there are no more questions in the chat, I will leave the stage